Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at the streams and flooding assignment. Alright, so the streams and flooding assignment consists of two parts. There is a Word document and there is also a PowerPoint presentation. Now the PowerPoint presentation is associated with pages 1 and 2 only. Okay, so you can see that on page 1 we have a range of questions coming from 1 to 12. These questions are all very simple and they are all based on the PowerPoint presentation. So if you read through the PowerPoint presentation, you'll be easily able to answer the questions. The one challenging question is going to be question number 8, where it asks you what is the total discharge for Blackwater River in Andover, New Hampshire. Okay, so how are we going to work that out? Well, if you look on page 2, there is a table, and it is a very, very empty table, unfortunately. So where is the information that we need to fill out this table? Well, it's in the presentation. So if we work our way through the presentation, we are going to come to slide 7. Slide 7 begins to teach us about how we actually calculate the discharge for a river. So when we were discussing the discharge in the presentation, we discussed the discharge as simply working out the area by doing depth multiplied by width, weren't we? So that would be fine if your river was a perfect rectangle or square. However, most rivers aren't. So how do we actually calculate the true discharge of a river? Well, what we do is we calculate or split the river up into lots and lots of separate slices. And we take the velocity, and we take a velocity measurement for each of those slices. And so what we're going to do is we're going to use the area of each slice and its velocity to calculate a discharge for each slice, and then we add all those slices together to give us the total discharge for the river. So as you can see marked here in red, this is one of the slices, so we'll calculate the area for this slice. We already have the velocity for that slice, so we have the area, we have the velocity, so we can calculate the discharge. We do it for all of them, and therefore we can then add those all together to get the total discharge. So relatively straightforward. So the final remaining question is how do we calculate the area for each slice? Because you can quite clearly see this isn't a rectangle or a square. So the way we do it is we actually calculate the area based on a trapezoid. Okay, so a trapezoid is simply b plus d divided by 2 multiplied by e. It's a relatively simple calculation. So the question then becomes well, where do we get the information to fill out the missing values? Okay, well on slide 9 you can see an example where they've already worked it out for you. Okay, so they have the diagram in the background that the table is based on, they have the table itself, and they have the calculated answers here in orange. Okay, so yellow is the information you'll get from the table, and orange is the information you will calculate. So for instance, if I wanted to calculate the area for this slice here, what would I do? Well, first of all, I need to know the depth. I need to know the depth on this side of the slice and this side of the slice. And obviously I know the depth here is going to be 0, so that's relatively straightforward. And I know the depth here is going to be 0.18. So there's depth 1, 0. Depth 2, 0.18. The other thing I know is I want to know the width of the slice. So it goes from 0 to 0.5 meters. So I have the distance, the depth on one side, and the depth on the other side. And I can use that to calculate my area using the trapezoid area calculation, which we can see down here. So we do that by doing A is going to be depth number 1. B is going to be depth number 2. And H is going to be the distance. And that's it. Now, when you do this calculation, please remember to make sure you add A and B together first before you divide by 2. And do this part of the calculation before you multiply by H. Otherwise, you will get an incorrect answer. So if I'm doing this calculation, I would do 0 plus 1.8, so that's that part there, sorry, 0 plus, sorry, let's try that again. 0 plus 0, 1, 8, which would be up here. Then I would divide that number by 2. Then I would multiply that number by the height, which would be 0.5. And then that would give me 0.045. And that would be my area. Now when I come to do this slice here, what are my values? Well, I need to know the height, the depth, sorry, on this side of the slice, which is 0.18, and the depth on this side of the slice, which is 0.24. So it becomes depth 1 is 0.18, depth 2 is 0.24. The width, well, the width is half a meter coming to 1 meter, so the total width here is half a meter again, because as you can see the increment has gone up by half a meter. So I have my depth 1, my depth 2, and my distance. So once again the calculation is 0.18 plus 0.24, divide that answer by 2, and then multiply that answer by the distance, 0.5. And that will give you 0.105. So as you can see, calculating the area is quite straightforward. So what about the velocity? Well, the velocity, as you can see, is given to us as a number which is written in the center of each slice. Okay, so as you can see, the velocity for this slice is 0.1 meters a second, this slice 0.23, this slice 0.14, etc. So what you'll do is you'll just simply write the velocity in the velocity column, and then calculating the discharge is simply the area you calculated multiplied by the velocity. Done. And that will give you the discharge for that one slice. Remember, you have to calculate discharge for all the slices, and then you add the discharges up at the bottom to give you the total discharge. So the total discharge is all of these numbers added together. Typically when you calculate a discharge, you should probably go to 3 decimal places. Although in some cases, if you have a number that's 0.000001, you might have to increase that number of decimal places slightly just to get the first digit in. Okay, so this is how we calculate it, and I hope this has made sense to you so far. So what do we do next? Well, this table here kind of shows you the kind of information that we get. Now this is for this would have been part of the exercise, but I cut it out to save a bit of time, and the data we're actually using is on slide 11. So here it is. This is the data that we'll be using to do our calculation. Okay, so as you can see, this is our river channel, and you can see it's cut into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 segments. So how do we get the information we need? Well, as you can see, the velocities are given to us. So we have the velocities, that's easy. What about the distance? Well, we can quite clearly see the distance is 0.5 meters for each segment, isn't it? Because every time we go from one to another, we're going up half a meter each time. Okay, the only difference is this segment over here, which appears to be about 1/4 of a meter, so 0.25 meters. What about the depth? Well, you're going to read the depth off this column over here. Now, when you're trying to read the depth off, don't try and overcomplicate it, okay? Depth value should be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Don't start trying to do, 0.275. You're overcomplicating the matter, okay? So try and keep it 0.1, so 0.01, 0.02, 0.0. So let's try that one again, shall we? 0.1, 0.2, 0.3, 0.4, etc. Just like it shows you on the axis here. So if we were calculating this first segment over here, well, obviously the depth on this side is going to be 0, and the depth on here is going to be 0.3. So our calculation to calculate the area is going to be 0 plus 0.3, divide that number by 2, and then take that answer and multiply it by the width, which is going to be 0.5. 0.5. I do apologize. Let's try that one more time just to make sure it's clear. So it's going to be the depth 0 on this side, plus the depth on this side, which is going to be 0.3. Add those two together, divide that number by 2, and then multiply by the width, which is going to be 0.5. Then once you have that area, you will then multiply it by the velocity to give you the discharge for this one segment. And then you move on to the next segment. So segment number 2, the depth on this side is going to be 0.3. The depth on this side is going to be 0.6. So in order to work out the area, that's going to be 0.3 plus 0.6. Divide that number by 2, and then multiply by the width, which is going to be 0.5. So that's your area. And then you're going to multiply that by the velocity, which is then going to give you your discharge. And so if we come and look at the document itself, we can see we have distance in one column. This is going to be the distance for each cell, so essentially 0.5 meters each time, with the exception of this cell over here, which is probably going to be about 0.25. We're going to have distance 1, and that's going to be the depth on the left hand side of each cell. So for the first cell it's going to be 0, for the second cell it's going to be 0.3, for the third cell it's going to be 0.6, etc. Then we have depth 2, that's going to be the depth on the right hand side of each cell. So for the first cell that's going to be 0.3, for the second cell that's going to be 0.6, for the third cell that's going to be 0.9, and so on. The area you will obviously calculate using the trapezoid calculation, and you're going to calculate the area by taking depth 1, adding it to depth 2, taking that number, dividing by 2, and then multiplying that by the distance, and that will give you the area. Make sure you do it in that order. Add the two depths together so you get it, and then get that answer. Then divide by 2 to get the second answer, then multiply by the distance. Don't try and type it into your calculator all at one time unless you're using brackets, because you will get an incorrect answer. Okay, so please make sure you do it step by step. Don't try and rush it and plug it all into your calculator in one go. Once you have your area, you take your velocity value, which is being given to you on the diagram for each of the cells. And then you take your area, you take your velocity value, multiply the two together to get your discharge. Your total discharge is simply all of these values added together. When you're writing your values in this column here, try and keep them to 3 decimal places, unless of course you have a situation where it's 0.00001 or something like that, in which case feel free to go to 4 or 5 decimal places just for those slightly longer answers. Okay? And so this is how we actually calculate realistically the discharge for a river. Now, please make sure you do this. Please make sure you do it well, because this is the kind of question that could turn up in exam. This is the kind of question I might ask you to print off, do at home, and then submit into a Dropbox as part of either the chapter exam or part of the final exam maybe. So what's on the next pages? Well, the next pages, page 3, is to do with recurrence intervals. So now we're on to flooding. So essentially, once you've done pages 1 and pages 2, this presentation is no longer required. So on to page 3. Well, on page 3, what we're going to do is we're going to try and calculate the recurrence interval. And as you can see, we have 4 distinct sets of data. We have this set of data here, Mercer Creek dataset 1. We have Mercer Creek dataset 2, Green River dataset 1, and Green River dataset 2. Okay, these are separate tables of data and you will calculate them separately. So how are we going to do that? Well, the first thing we're going to do is we're going to rank the size of the discharge. So, okay, so for the peak flood discharge, we're going to look for the largest number. What's that going to be? 254 there. Is that going to be the largest? Let's just double check. Yes. And so the largest one is going to get the rank of 1. Excuse Rupert in the background. Then we are going to steadily rank the floods, going from 1 being the largest to 11 being the smallest. So the smallest discharge is going to be, let's see, 150. Let's just double check. Good. So that's going to get rank 11. And you're obviously going to fill in the ranks in between. So each one of these is going to be ranked somewhere, a number between 1 and 11. Now from that we can do our recurrence interval calculation. So the recurrence interval t is calculated by n, which is the number of data points you have. So in this case the number of data points is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So for each of these tables we have 11 data points. So n is going to be 11 plus 1. Then you're going to, once you've done that calculation, you're then going to divide by m. And m is your rank. So whatever number you have here. So for instance, for 1963, your calculation would be 11 plus 1, so 12, divided by 11. That simple. And you're going to do those calculations for each of these 4 tables. Now over here on page 4, what I've done is I've taken this data and I've used this data to extrapolate the size of a 100-year flood. So over here you can see we have 100 years. And so this data point here would represent the predicted size of a 100-year flood. So on page 5 here, you can see I'm asking you to look at each data set and I'm asking you to predict the discharge for a 100-year flood. Now over here we have the discharge values. Now this upper graph here is Mercer Creek 1 and Mercer Creek 2. So Mercer Creek 1's in blue and Mercer Creek 2 is in red. And on the lower graph here we have Green River 1 in green and Green River 2 in yellow. And so for each of these trend lines you're going to look and you're going to see, right, that's where it hits 100. I'm going to come across here and I'm going to read the value off over here. And that's the value I'm going to put into this table down here. And that's going to be my predicted discharge for a 100-year flood. Next, we're going to look at the data itself. We're going to say, right, how do the discharge graphs for the 2 rivers compare? Okay, now remember we're comparing the same river. So you're going to compare Mercer Creek 1 to Mercer Creek 2 for this answer, and Green River 1 to Green River 2 for this answer. So we're going to describe very concisely what the difference is. So for Green River 1 to Green River 2, okay, remember this is the earlier data set, this is the later data set. So did the discharge go up or did the discharge go down? And your answer has to be that simple, i.e. it went up or it went down. That's it. Question 3. Suggest 3 possible activities for each river that could have caused the differences in the predicted floods. So for Mercer Creek, we can quite clearly see that there has been a change in the discharge between this data set here and this data set here. And so the question is, what could have caused this data set? You're going to give me 3 possible reasons as to why we've seen this change in the discharge. Okay? Don't start giving me, weird explanations. Try and keep it to the things that we have in the lecture. Okay? Don't try and overthink it. So that should be 3 answers for the Mercer Creek and 3 answers for Green River. So 6 answers in total. Question 4. So based on the flood predictions for all 4 data sets, what does the contrast in predicted flood discharge imply about the usefulness of the 100-year flood as a legal designation for these 2 streams? Is it useful? So what I'm asking you here is, well, okay, here's data set 1 and here's data set 2. And they've been taken for different periods of time, haven't they? Different 11-year periods of time. And we can see that, well, this data set here gave us a predicted 100-year flood size there. Whereas this data set gave us a predicted 100-year flood size here. So the question then becomes well, is a 100-year flood a truly helpful thing? So, it's kind of dependent on the data you're using, isn't it? So you have to decide is that is that helpful, or is that something that in theory can be abused? So, is a 100-year flood, the idea of a 100-year flood actually helpful to us? So question 5. What is the probability in any given year that the stream discharge will exceed the discharge of the 100-year flood reoccurrence interval? I would advise you to go back to the presentation and look at the final few slides of part 4. And that's where we start talking about the probabilities of a flood reoccurring. I would advise you to go back, look at those slides. That would also be useful when answering question 6. And that's it. This is a very straightforward lab. Most of the marks are going to be in the calculation here and the calculation here. So this is going to be quite a mark-heavy lab. So I would strongly advise you to spend a few minutes doing this, making sure you get it right, because this lab is going to give you a nice chunk of marks. And that's it. There's not really much more explanation required. Just get it done well, and enjoy the marks that you get for it. All right. Have a good day, guys.